Hello everyone, I'm Elizabeth and we're going to look at friction today. So, what is friction? Now, number one, friction is a force. It's also a force, and it's a force that will always opposes the motion of an object. So if a force is working on an object where it pushes it to the right, then friction will also be a force, but it will always work opposing on the opposite direction of the direction of your displacement of your object. So friction is a force, but you're going to see we're going to determine there's two kinds of friction. A friction where the object is standing still, it's stationary, it's not moving, and friction where an object is already moving. Okay, why do I say that? I'm sure you have tried to push a heavy object before. Like, let's say your dad's car broke down, okay, and you need to push. So there's that big heavy car and you're pushing. But that car is not moving, but you're pushing. Let's say you start with 10 newtons, then you go to 20 newtons, then to 30 newtons. But that car is not moving. That friction that car is then experiencing is static friction. So the object stays stationary, it's not moving. So static friction can increase equally to the force that you apply. So let's have a look. So let's say you're applying, there's an object on a certain surface, and you apply a force, an applied force onto that subject of, let's say, 10 Newton. But that object is not moving. That means there's a static friction of the surface that works and operates parallel to the surface, but in the opposite direction. So it means there's a force that opposes you, which is, and we're going to write friction with such a small little f, and I'm going to say there's a static friction that is opposing that movement. And if I would push that up to 20, then that static force, and it's still not moving, goes up to 20. Now we can actually use a graph to show this. So let me just give you a graph, and we're always going to look at our axis, what is standing on our axis. So on my axis here is going to stand my force in Newton that I applied. So it's basically applied force. And on this axis, I'm going to have my friction force, also a force. Now this is exactly what's happening now. So let's say an object stays stationary. So I'm pushing as hard as I can. Let's say I start with 1 Newton, then it's still not moving. That means that there's an opposing force, in this case friction, static friction, between my object and its surface, working parallel to the surface in the opposite direction of my applied force. And let's say I start pushing by 2 newtons, so 1 newton, 2 newton, 3 newton, 4 newton, 5 newton, and so on. Then it will just go up. That object is not moving. So my friction increases. But what friction is this now? If I push with 2 newton, the friction is 2 newton. If I push with 3 newton, it is 3 newton. So it goes up, up, up. If I push with 4 newton applied force and that object is still not moving, it's going to mean that the static friction is also 4 newton. But then it comes to a point, so you're pushing, push, and the moment that object is starting to move, like in a heavy car, all of a sudden it just goes easier. It's much easier to move an object that's already moving. And you're going to see the reason why, because the friction changes. At the moment, so it reached a point here, which we're going to call F is max. So So that is the maximum point where that friction, static friction, is working or opposing me in the opposite direction for that object to still stay stationary. If I then increases to 5 Newton, my applied force, and that object starts to move, in that split second where it's starting to move, let's say that is the point 4 Newton is the maximum static friction working against me, it's going to drop immediately, and then my friction of that object, once it starts moving, stays the same. So when that object then starts to move at a certain constant speed, then and now what we're going to call it, we're now not going to call it static friction, then we're going to say, now it is my kinetic friction. So it's a friction that is the force that opposes any movement of an object, and it opposes it and it works parallel to my surface but in the opposite direction. So frictional force is only when that object is already in movement, and static friction is when that object is standing still. Okay, so now we're going to say, all right, if that is what is friction, so friction is the force that is opposite your applied force. So you need to know in which direction an object is moving for you to know in which direction the friction is going to work. Okay, now let's go back and try and find a formula in which we can work out the amount of friction. So let's start just with, what do you think if I have an object here and I'm saying to you this object is of course not frictionless. So if I put my fingers over it, I can feel this friction, all right? So let's now say I want to determine or find out what will be the formula to work out the friction force. Now let's say friction in general would always be equal, directly proportional to what? To what? To that surface, of course. If this surface is really rough, then that friction is going to be more. So, but it's always two surfaces working on each other. So let's say I've got this object, okay, I've got this plank of mine, and I've got a different object. So there is going to be a roughness between the two. Now what are we going to call that? That surface, the roughness of the surface. We're going to call that the coefficient. And that's going to be, we're going to use a U that looks like that. Now that coefficient is always going to be a constant depending on the sort of material that the surface is made of. It could be, of course, I could use my calculator and this surface, and immediately I've got a different coefficient. So that's a new word that we're going to learn now in physics in grade 11, all right? And that is the word coefficient. So it's a constant, but it depends on what? Of course, on the surface of the two objects that's going to glide over each other, all right? So that we can either work out or they're going to give it to me. So that is actually not so difficult. Now that coefficient is not going to have a unit. And I'm going to come back to that. It's just to say how rough the subject is. Is it very rough, not so rough, whatsoever. So the coefficient only is going to tell me something about the surface of the two objects moving over each other. But what else do you think is going to determine the friction? If it's big friction or a small friction. If I look again at my plank, and I've got again my object moving over my plank, okay, you might use my hands, okay, I've got something that's moving, so my fingers is just going to go easy sliding over the object very lightly. Yeah, there's friction, I can feel it. But what if I'm going to push harder? Yes, the friction increases. So that tells me that friction is also equally directly proportional to the normal. Why the normal? Because if I have an object here on a certain surface, the amount or the force that I'm going to push it down onto that surface, and we know that that normal equals, that is actually my normal. My normal is always the force working upwards from the surface upwards, which equals the force with which I was pushing it down. But we're not going to work with the force that I pushed it down with. We're going to work with the normal. And there we've got our formula. So now we can immediately say, oh, friction equals the coefficient, that is the surface on which it is moving, times the amount that I am pushing hard onto that object, the normal force. Now we're going to break that up, of course, in the two types of friction. So we've got our static friction, and we're going to always, when we work with static friction, we're going to only work with the static max. So that means that maximum point, the moment just before it starts to move. So I'm going to say Fs, small s, and I'm going to say max. That means that my static friction, and that is when my object is still standing still, stationary, it's not moving. So that moment just before it starts to move, and that I can then work out with my coefficient, and that is a different coefficient when something is standing still or when it's moving. So the coefficient is changing. There's always going to be a coefficient for static, object stands still, or the moment it starts to move, that coefficient becomes smaller. Why? Because we saw that it's much easier when an object is already moving. Alright? Then the friction is less. So my coefficient becomes less the moment an object is already moving. Okay? Times my normal. So there I've got my formula to work out my static friction, but friction max. Because why? I don't know. If I'm pushing with 1 Newton, it's going to push back with 1 Newton. Increase to 2 Newtons, increase to 2 Newtons. 3 Newtons, 3 Newtons. So I have to say, okay, but which static friction are you talking about? The one that is operating against that static object from moving. And it's that maximum amount of static friction. All right. And then we've got our kinetic friction. Oh dear. Can't spell. Kinetic friction. And here our formula is going to look pretty much the same, except that we're going to use now Fk. K stands for kinetic. That means that object is already moving with a certain constant speed. Could also accelerate, but it's already moving. And that would then equal, and now we've got a different coefficient. That is for when the object is kinetic, it's already moving, times my normal. So there are my two formulas that I'm going to work with when I have to determine the amount of friction that an object experiences on moving over a certain surface. Great. So let's go back to my formula. Okay, so I'm just going to, and remember guys, you need to know these definitions out by heart according to your exam paper or your I'm sure they're going to give that to you on a certain paper or on a data sheet or in your textbooks. Please know these these definitions for kinetic friction, for static friction out by heart. Okay, I want to now focus on the normal, because this coefficient, like I said, will either be given to you and it's always less than 1. So it's always going to be, let's say, a number like 0.2 times if it would have been completely frictionless. So it's always actually just shows you a relation. And that's why there's no unit. But if they want you to prove why is there no unit for the coefficient, I want to show you this. Let's take that coefficient, okay, and we get it on its own. Could be coefficient K for kinetic coefficient. So we've got here a K and the normal. So what do I do then? I'm going to say it equals my kinetic friction divided by my normal force. Now what do I measure friction in? Friction is a force. I determine that in Newton. That's the unit for force. And my normal, oh, that's also a force. Oh, so that's also Newton. So what happens here? My newtons gets fallen away and my coefficient has no unit. All right, but let's go back. So what I want to show you is that my problem when I work out friction is going to be determined by the normal. Now let me show you 4 different scenarios where you have to work out the normal and it's different. So let's start with the first scenario. Let's say I've got an object that is just onto the surface and you are just applying the force and the object is moving over the surface. But it's just straight there, so there's my force, my applied force, and now I need to work out the normal. So let's go for it. So I have my opposite direction, my frictional. I've got my normal force going up and I've got my gravitational force Fg going down. So what do I see in the y-axis? I can see that my normals, okay, now first, how do we start? We say my net force on the vertical axis is 0. So F net is 0. Why is that? Because vertically looking, that object is not moving either up or down. It stays on the surface. So the normal force then equals the gravitational force, and that results then in a net 0 Newton. So then I can say, okay, so it's normal minus Fg equals 0. So my normal equals my mass, my Fg, gravitational force, which I can work out with mass times gravitational acceleration. So there, in this scenario, I can then have my coefficient, they give that to me. I have to then work out what is my norm and my normal force. My normal force will then equal the weight m times g. Okay, so that is scenario number 1. Scenario number 2 looks like this. Again, I've got my object. Okay, it's again moving horizontal parallel to the surface, but I am pushing it with an angle. So let's say my applied force is now with an angle of theta degrees. So how do I determine my normal now? So let's go back to my body diagram. So what I have is an applied force but with an angle. So I can then say, all right, can I get the 2 components of that force? Yes, that's my Fx and that's my Xy. If I move that Fx just towards here, it means I've got a horizontal force, a component of that pushing, which is working horizontally and the object is moving horizontal. So I've just picked it up and put it there, okay? But I've also got a y component of that force, which means that I'm actually pushing down into the surface that object. But if I lift it up and put it here so that we have them all working on the same point, there is my Fy. So that is when I have a force that works let me just make it as a dotted line, where it's pushing downwards onto the object. Object as displacement is forwards, but now I have basically two components. One component is pressing that object onto the surface, and the other is making the object moving over the surface. So these are those two then. Okay, so what else is there? Yes, there's the normal force working upwards from the surface onto the object upwards. And yes, there is the weight of that. Let me just make my dot a bit bigger. By weight of my gravitational force, Fg or W, as some of you already starts to use in the school. They want us actually to change over to using only W for weight. Alright, so what do we see now? Again, if we look only on the y-axis, okay, what is all the forces that's working so vertical? So it's still not moving up or down, which means F net equals 0 vertical. But what is the forces working vertical? It's the normal force. And let's say I choose up as positive. That means it's a plus N. But that force is working in the opposite direction, so it's plus minus Fg or weight, plus opposite direction minus Fy equals 0. So now you can see that my normal equals, if I take that to the other side, it will be my weight plus that vertical component. So now you can see that the normal force actually increases when you have an angle and you push onto something, because there's a y component that's going to add to the weight. Here it was only the weight. Now it's the weight plus that vertical component, Fy. So now I've got to work out the normal force. That's going to be the mass times gravitational force, plus again, how do we again work out the vertical here? It's opposites from there. So yes, I can remember we had it in components. It's going to be my applied force, F what? Sin theta. Alright, so it's going to be mass times G plus F sin, that's the angle with which I'm pushing, sin theta. And that is what I will then use in my formula there. So you see, now it becomes slightly complicated. So not really complicated, just stick to drawing your forces in a force diagram and then get your normal force. Alright, so that's scenario number 2. Scenario number 3 is very similar, but instead of pushing it, I'm going to pull it with a certain angle theta. So that is my applied force. So my object is not going to lift up from the object, from the surface. It's still going to glide over the surface. So I'm still going to have movement in that direction. So if I'm going to look at what is the forces working here, it is my Fx, which is that Fx component. It is the Fy of the applied force. Now I'm going to take it away. So now the applied force is broken up into a y component and an x component. I still got my normal force here, and I still got my weight or my gravitational force working downwards. But what do I now see? I say, okay, it's still not moving. So my resultant force or my net force vertical is still 0. Why? It's not moving up or down. So we're just going to look at horizontal, but not now. Okay? For normal force, which works vertical, we're only going to look at the vertical forces. Okay? So what do we have here now? Again, if we use up as positive, it means that it is plus n plus Fy minus Fg or W equals 0. So now my normal force would be my Fg, gravitational force. If I take it over, it becomes a plus. The plus becomes a minus my vertical component. So that would be mass times gravitational acceleration, mg, minus, what is my vertical component? It's going to be F, my applied force, sin theta. And now I want you to see something very important. Why is it easier to pull, let's say, a lawnmower over the grass than to push the lawnmower over the grass? And you know what you're going to do? We're always going to come back to this, because when I push it, the y component is actually pushing it into the surface. So my normal force is going to become bigger, because now it adds to the weight of that object which was there already. So it's the object's weight plus the normal force, so that's really big. So my normal force that works in the opposite direction is going to be increase. And what do we see? If my normal force increases, my friction increases. And as the friction increases, it's going to be more difficult to push that object, because that's a frictional force, always works opposite direction of where I want it to move. So by pushing it, I'm pushing it right into the surface, my frictional force is going to increase. Whereas if I would just pull it, I just take the lawnmower and I just pull it over the grass, what's happening now? It's just going to boom, boom, boom over the grass. It's not going to be a very good grass cutting job, that I can tell you. Why? Because now, as you can see, what happens with my y component? My Fy component works now upwards, so you're actually lifting that object away from the surface. And by lifting it away from the surface, my normal force is going to decrease. It's going to become less, because it's the weight minus the fact that you're actually lifting it up. So it's not the weight just pulling it down, you're actually lifting it a bit away. And the moment my normal force decreases, my friction is going to decrease. And therefore, it's going to be much easier to move that object, lawnmower, over the grass. Okay, but because you are not really going onto the grass, it's not going to cut very well. So don't use that technique. All right, so that was the third scenario. Now let's look, so just to recap again, the three ones. Object just resting, okay? And the applied force is in the same direction as the displacement. So I'm pushing over under friction, so they're both working in the same angle. Here I've got the friction that's going to opposing me parallel to the surface, but my applied force come in with an angle, either pushing or pulling it with an angle, which means I will have to get to my normal. I will first have to see, okay, there's also a Fy component. In the case of pushing, I have to add the Y component. In the case of pulling, I'm actually going to deduct the Y component. Okay. Now the fourth scenario looks like this. So these two in my books are the more difficult ones. The ones pulling, the applied force comes with an angle, either pulling or pushing. Okay, so now let's look at the fourth scenario. And I'm sure you're guessing it because we did it already. Okay, so the fourth scenario is where I've got an object and it is on an angle. So my surface is at let's say an angle to the horizontal of, let's say, 30 degrees. So now if I would have an applied force, let's say I've got an applied force, I'm pushing this object over the surface upwards, then my friction is going to go in the opposite direction. So let's say that is my F applied force. So my friction, F kinetic, if it's moving, its kinetic force, will always be parallel to the surface down. Now again, I need to get to my frictional force here, I have to determine what is in, because that coefficient they're probably going to give me, so that's easy peasy, I get it. Okay, because I don't know what the coefficient of every single surface there is, so they have to give it to me. Of course, I can also work it out if they give me the frictional force and I've got my norm, then I can work that one out. Okay, so let's get back to the scenario. So, where's my normal force now? Now, remember, my normal force is going to act 90 degrees to the surface. So, normal force on a flat surface is going to be always 90 degrees to the surface. Even if I now move that surface to a certain angle, so it slopes with a certain angle. So this is my normal force. Now I hope you can remember that we can, with weight, have an x and a y component of weight when we are on a slope. And what is that again? So that would be then operating there, exactly in the same plane or axis, is my weight, or my Fg, perpendicular to the surface. And I've got a component of my weight of my object, Fg, parallel, or Fg, perpendicular. No, sorry, not perpendicular, parallel, not Fg. Oh, sorry, I wanted to use W for weight. So I've got my weight, which normally would work straight down to the center of the earth. But, you remember, with components on a slope, I can break up those two components in a perpendicular and a parallel to the surface. Okay, now if I have this, remember I can work out F or W by saying it is my weight mg, and I'm always going to say cos theta for perpendicular on the table. I always think about this food on the table. Cos, I know is Afrikaans word for cos, food, whatever, so we're going to say cos theta. So it's the mass of that object times 9,8 cos that angle of the slope. Whereas if parallel, as you can remember, so weight parallel equals my weight mg sin theta. So I'm always going to work with sin theta. The reason again is if something slides down a slope, I always imagine it's going straight to hell. Why? Because it sinned. It has sinned. So that's how I remember I'm going to use sin theta for that component. But right, we're now not interested in that. We're interested in the normal force. So what is the normal force going to be equal to? As you can see, that object is not jumping away from the surface, it's not breaking the surface. So in that plane, there's an equilibrium. So in that plane, we can say again, F net 2 equals 0. What is the two forces there? It's my normal, and in the opposite direction, minus my Fg, perpendicular, equals 0. So my normal force would be, what is it again? My mass times gravitational acceleration cos theta. So if I have something on moving over a slope, then my normal is always going to be my weight cos theta. And then I'm going to just use that, put it in my normal, and I can work out what is the frictional force for moving over a slope. Alright, so let's stop it there, because that is, I think, enough for one day. So just to recap, you get two frictional forces. Okay, the one is for an object that is stationary, But I just want to emphasize, if an object is standing still, but there's no applied force working onto it, then there's no friction either. So there's only friction the moment I start to push, even though it's not moving. But then if I have an applied force, that means there's a static friction working in the opposite direction. And then it gets to a maximum static friction the moment that object before it starts to move. And that is then, that after that, so that the moment the object starts to move, it's going to experience kinetic friction. We're going to use the same formula. Just for kinetic friction, we're going to use the small k. And for static friction, we're going to use Fs max. And there I'm just going to have a different coefficient. So the coefficient just is going to tell me something about the surface, okay, how rough the surface is, and the normal force is going to tell me how hard do I push against that surface. All right? So that is the start of friction. In my next lesson, we're going to look at how do we work out typical questions. How are they going to ask me? How am I going to have to work this out? All right, but believe in yourself, you can do this.